Okay, so let's just start this second video by just writing the last expression that we wrote for the previous one, which was the internal energy change in a process, that any process that takes you from equilibrium state A to equilibrium state B. We just decide to write it as the work that you do on the system plus something else. Okay, so remember that what this means is that, okay, you first take your system from initial state A to initial state B by doing a process when the system is enclosed in an adiabatic container. And what you do is you make a note of how much work you had to do on the system to create that. And this is equal by definition to the internal energy difference between states B and A. Okay. So then what this expression means is that if you were to take the same system from the same initial state A to the same initial state B, but without the adiabatic enclosure, so you allow for heat exchanges, then you will see that the work you have to do in general is going to be different from that. Okay, so if this is the case, you just call the difference between the actual work that you do in a non-adiabatic process and the adiabatic work, you call it heat. Okay, and in this video I'm going to try to convince you that it makes sense to think about this difference, about this Q, as heat, as the heat that we introduced in the first chapter of the temperature. Okay, so let's see how this is possible, and we're going to do that by thinking of the classic experiment, the historical experiment by Joule, when he calculated the work equivalent of heat. So, okay, what we have is a calorimeter. Okay, so remember from the first chapter that the calorimeter was adiabatically insulated container, and I'm going to just draw it as a double layer. So just a second, I will do something like this and like that. Well, that's already good. So this is, imagine an adiabatic container, and inside of it I'm going to put some calorimetric water. So there is a known amount of water inside of the container, and there is also a thermometer that tells me what the temperature of the water is. Okay, so I can look at this thermometer to know the temperature of my system, and imagine, just for concreteness, that I have 1 kilogram of water, and that the initial temperature of my initial equilibrium state happens exactly to be 14.5 degrees centigrade. Okay, and then what I will do is I will insert a system here. So this is like a paddle wheel. Okay, so I have some kind of spinning thing that contains some wooden paddles like that I'm going to rotate around. Okay, so something like this. Some solid wooden panels here, and this thing, like I say, it rotates. Okay, and it has an axis that looks terrible, but you have a nice picture in the lecture notes, actually an original engraving from when they were describing the experiment. Okay, so you have these paddles in here, and there is like a length of rope tied in this cylinder, and this rope is, if you like, connected through a pulley to a mass, and this mass is falling, right? And because the mass is falling, well, you get some motion of the paddles, and the paddles move against the friction with the water, and they create some turbulent flow here, and they create they dissipate because there is friction being made. Okay, and what will happen is that the temperature that you observe in your calorimetric water in the end of the experiment, well, it's going to go up, but you just decide to stop your experiment whenever it reaches 15.5 degrees centigrade. Okay, so it goes up exactly by 1 degree. Okay, so here you see that the calorimetric water, by definition of what the kilocalorie was, or the large calorie, has absorbed, this water has absorbed 1 kilocalorie in this process. Okay, but there is no exchange of heat. This water, like I said before, is within an adiabatic enclosure, and there is no exchange of heat whatsoever with it. The only thing we are doing to the water is work, mechanical work. Okay, And with this mechanical work, we are injecting into the water 1 kilocalorie. Yes. So, okay, that makes you think, yeah? Because alternatively, you could have removed the adiabatic enclosure and you could have brought your mass of water in contact with a heat source which is already at the final temperature, and you wait for thermalization. And then, when you observe that the temperature of the water goes up by 1 degree, what you would say is, yes, of course, because the water has absorbed 1 kilocalorie of heat from the heat source, okay? Here there's no heat source, and the water is doing the same thing. It's arriving to the same final state, and the only thing you're doing on it is work. So then work and heat must be equivalent, because doing work only or doing heat exchange only, you can take your system from the same initial state to the same final state. And in other words, you can achieve the same change in internal energy, okay? Because we know the initial and the final states are the same in both experiments. When we have the paddles moving, yes, we know that the change in internal energy by definition is the adiabatic work that I do to go from initial to final, yes? And when I write it like this, I know there's no heat, okay? And in the second experiment or thought experiment that I'm proposing you, there is just the heat source in contact with my system, and there is no work being done at all. There's only heat, okay? So I have able to make the same change in internal energy of my water by only doing work, and on the other hand, by only doing heat. So this means that heat and work are kind of in the same footing, and this leads us to the first law of thermodynamics. Sorry, I'm missing an S here, okay? So this is, if you like, the integral form of the first law of thermodynamics. You can also write it in a differential form like this. And what I wanted to highlight from this is that the work we saw before, it is not state variable, it is a process variable. And this is why we write infinitesimal increments or infinitesimal amounts of work with this delta symbol, because it is an imperfect differential. The same thing happens with heat, okay? None of them individually is a variable of state. However, if you add the work and the heat done while you connect any initial state with any final state during any process, well, that sum is going to be constant. It doesn't depend on the process. It only depends on the initial and final state that you fix. So the sum of these two process variables gives you state variable. Okay, so that's important to bear in mind. And to conclude this video, actually just a final comment, which is on the units of heat. So when we introduced heat here, we really didn't say what were the units of heat. We just defined this kilocalorie, but we didn't know what place heat occupies in the international system of units or anything. Now we see that heat can be measured in joules, yes, in the same units as work, because it's equivalent to work. So in this experiment, Joule actually was able, by looking at the change in the mass of this falling weight and the loss in potential energy, and neglecting any friction and any losses, he was able to estimate how much work he had to do on the calorimetric water to raise its temperature by 1 degree. And therefore, he calculated the work that is equivalent to 1 kilocalorie, and this is 4,200 joules. This is equal to 1 kilocalorie. So kilocalories are actually joules. It's another way of measuring work. Okay.